Alrighty, so we have gone through several series tests. Today, we are going to learn about the comparison test. There are two. So as you can see, we have done the geometric series test, the telescoping test, the nth term test of divergence, the integral test, and the p-series test. Today, we're going to do the direct comparison test and the limit comparison test. And today we are going to learn how to use comparison tests to test to see if a series converges, and then also to use the limit comparison test to determine if a series converges. Now, I could tell from grading your exams that some of you have seen these tests before. And as I looked over your test, I could see that they're trying to use these tests, and we weren't quite ready to use some of these tests. So before I get started on the next two tests, I'd like somebody to tell me some information about the geometric series test. What can you tell me about the geometric series test? Anybody? Or the telescoping series test, or the nth term test of divergence, or the integral test, or the p-series test. I would like you to please tell me some information about these tests.
Um, I could tell you about the telescoping
Okay.
series test. One way I remember it is because it uses partial fractions.
Okay, very good. All right, so telescoping series test does use partial fractions, and many times it will be given to you and you won't need partial fractions because it'll already be separated into a fractional expansion, but if not, you will need to do so. Okay, so that's excellent. Thank you, Peyton. Anyone else? Okay. Well, you are going to need to know something. This test, the geometric series test has a particular form. You should know what the form is. The geometric series test is also summable if the absolute value of the R within the expression is less than 1. Okay, Peyton told us about the telescoping series test, the nth term test of divergence. That test only tells us if the series diverges, does not provide information on convergence of the series. The integral test, you can compute a similar integral. And if the integral converges, the series converges. The integral diverges, the series diverges. And then the p-series test, also of a certain form, and it converges under what condition for p? I'm not writing this down because I'm trying to let you guys visualize what you already have seen. So I want you to start to be able to visualize these things. So what does the p-series test give you?
If P is oh, if P is above 1, it converges, and if it's at 1 or less than 1, it diverges.
All righty, thank you. Okay, so let's look at the limit comparison test. The direct comparison test. I think you will like these two tests. I remember when I learned them, I thought the direct comparison test was a pretty cool test. So we're going to do that first. All right, so that's test number 6. And here it is. We have two series, summation AN and summation BN. All right, both of these are series. Okay, they have positive terms. If you notice, AN and BN are both greater than 0, but more importantly, Bn is bigger than An. So all the terms are Bn are bigger than An. And this is after a certain point in the series. It may not be true at the beginning, but after a certain point, you can always say that 0 is less than An is less than or equal to An, less than or equal to Bn. Okay, so here's the test. If summation Bn converges, that is the larger series, then of course the smaller series, the summation An, has to converge. And if the summation An diverges, that's the smaller series, then the summation Bn also diverges. Okay, so if you can take your series and make it smaller than something that converges, you know it converges. If you make it larger than something that diverges, then you know it diverges. Okay, so our first example is this series. Whoops. New computer, still getting used to it. Here we go. Okay, so this series summation, notice it is n equals 2. I can't use n equals 1 because n equals 1 would give me a 0 in the denominator. So this series starts, its first term is when n is equal to 2, and then you can write this series out. Okay, so now what I want you to do is think about what this series looks like, because we're talking about, we're going to do the direct comparison test. So I need to be able to make 1 over n minus 1 smaller than something or bigger than something. So let's just start off with n minus 1. Okay, so we clearly start off with n minus 1. And n minus 1 is always less than n. It's always less than n. Okay, doesn't matter what n is for n, all n, n minus 1 is always less than n. So what does that mean? If I take and I do a fraction, I have to do the reciprocal. So I get 1 over n minus 1. This now becomes larger than 1 over n. Okay, so now I have two series. So I'm going to write this as an. It's going to be the smaller series, 1 over n, which is less than 1 over n minus 1, because the denominator is smaller, so there the fraction is larger. And this is equal to Bn. So I have exactly the case where I have one series less than another, and this one is not even equal, it is strictly less than. Okay, so this gives me right here. Oh, that's why I keep getting that, because that's in the way. Move it. Let's move that. There we go. Now I can. Okay, so this gives me directly that an is specifically less than bn. Okay. Okay. All right, so now that I have an is less than bn, let's look at what my theorem says. My theorem says, or my definition says, if I have two series and Bn converges, then An converges, or if An diverges, Bn diverges. So let's look at summation An. So summation n equal 2 to infinity of An is the summation n equal 2 to infinity of 1 over n. Now, what kind of series is 1 over n? That's a special series. In fact, it has a name. I know it doesn't start at 1, but it's still the same series. What is this called? Where have you guys been? Have you looked at this stuff over the weekend? Special series called what?
Harmonic series.
Okay, this is the harmonic series. And what do we know about the harmonic series? We proved this using the integral test. We used the integral test. Does the harmonic series converge, diverge, or we don't know? Wow.
Now, would it be inconclusive if, or they have to use a different type of test to calculate?
We don't have to use a test to do this at all. We proved this one. So the harmonic series, this series diverges. We proved the harmonic series diverges by using the integral test. Hence, we have the summation n equals 2 to infinity of 1 over n is less than the summation n equals 2 to infinity of 1 over n minus 1. Okay, so since the summation n equals 2 to infinity of 1 over n diverges, and the other series is larger than it by the direct comparison test, the summation n equals 2 to infinity of 1 over n minus 1 also diverges. Okay, any questions? Okay. No questions, no comments.
Can you go back for a second?
Oh, absolutely. I was just getting our next problem. Where do you need to be?
Right
Well,
there is good.
that's the whole thing.
Thank you.
Okay, number 2. Okay, what kind of series does this look like? Let's just say for a moment, n got really big. then the only thing that really matters is the n squared. So what kind of series does this look like? Okay, it kind of looks like a P series, where P is 2. Okay, so my brain is thinking, this thing might actually, okay, stop. This thing might actually converge because it looks like a P series, but we're using the direct comparison test. So let's see. We have n squared plus 6 is clearly bigger than n squared, and that's true for all n. No matter what number you pick, it's always going to be true. So therefore, let's take 1 over n squared plus 6. It is certainly smaller than 1 over n squared. Okay. So notice with the direct comparison test, you end up actually using 2 series tests. You're comparing it to one that you know converges or diverges, and then you're using direct comparison test to actually bound it by something larger or underbound it by something smaller. Okay, so I have that. So I'm going to let this be AN, and I'm going to let this be BN. Okay, so notice again, AN is less than BN. All right, so the series that I'm trying to figure out is BN. I'm sorry, is AN. And since AN is the smaller one, I'm hoping that the bigger one converges. Okay, so now let's examine the summation n equals 1 to infinity of 1 over n squared. What do we know about this series? 1 over n squared. What kind of series is this?
The P series.
All righty. So this is a P series. And what is P?
2.
P is equal to 2. Okay, so what do we know about that then? We have P is equal to 2. And what's the criteria? Malcolm gave it to us earlier. Malcolm, can you tell us what the criteria was?
When P is above 1, it converges, and when P is at 1 or less than 1, the series diverges.
Okay, so this series converges. Thank you.
So
Okay. Hence, now we have the summation n equals 1 to infinity of 1 over and 1 over n squared plus 6 is going to be less than the summation n equals 1 to infinity of 1 over n squared, which converges. So since the summation n equals 1 to infinity of 1 over n squared converges by the direct comparison test, the summation n equals 1 to infinity of 1 over n squared plus 6 converges. Okay, so that's 2 down already. All right, so this second series converges because it's less than a series that also converges. Okay. Number 3. Uh-oh, I forgot. I don't have to write number 3. I already have it. It's already prepared for us. Now this one is a little different. And the reason why this one is different is because we haven't looked at a series like this. This is 1 over n factorial. Okay. I could have even started this one at 0 because 0 factorial exists, but I'm not going to. So I'm going to write this one out. So it's 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, 1 over 5 factorial. Is that right? Yes. 1 over 6 factorial plus dot, dot, dot. Okay. So the terms seem to be getting smaller, but we already said just the fact that the sums go to 0 for us means nothing. We need to be able to use something. So I'm going to do a comparison. So I'm going to compare this, a direct comparison, to a series that I know converges. So I want to use the fact that 1 is actually equal to 1. And 1/2 is actually equal to 1/2. So far I haven't done anything. But let's use the fact that 1/6 is certainly less than 1/4. And 1 over 24 is certainly less than 1 over 8. And 1 over 120 is certainly less than 1 over 16. Okay, so if you haven't figured out what I'm doing yet, I'm going to start to rewrite it. So I have 1 is equal to 1. I have 1/2 is equal to 1. Oh, I know what I want to do. I want to write this as 1/2 to the 0 power. And this is 1/2 to the 1st power. And 1 over 6 is less than 1/2 squared. And 1 over 24 is less than 1/2 cubed, because that's what I have. And then 1 over 120 is less than 1/2 to the 4th. And I can keep going, and I can see that my general rule for this, I can see, is that 1 over n factorial is always less than or equal to 1/2 to the n minus 1. So it's equal to in the beginning, and it's becomes strictly less than. So now my an is going to be 1 over n factorial which is less than or equal to 1/2 to the n minus 1, which I'm going to let be my bn. So now I have an is less than or equal to bn, and I am happy because now that I have that, I now get, so let's, uh-oh. I have no idea what's going on with my pointer here. All right, so let's examine the sum n equals 1 to infinity of 1/2 to the n minus 1. So what kind of series is this? We've done this one.
Is this the Geo series?
Oh, it's got a nickname now. All righty. This is the geometric series with a nickname. This is a geometric series. And what do we know about geometric series? Okay, so here A is 1 and R is equal to 1/2. So that implies what? Does this series converge or diverge? You guys have not been hitting the books. All right, so this converges since the absolute value of R equal to the absolute value of 1/2 is less than 1. This was my prime example. In fact, this series has a sum. Okay, remember the geometric series, you can sum it, but I'm not worried about that right now. All I know is that this series converges. Hence, we have this. We have the sum n equals 1 to infinity of 1 over n factorial is less than or equal to the sum n equals 1 to infinity of 1/2 to the n minus 1. Okay, so since the sum n equals 1 to infinity of the bigger series, 1/2 to the n minus 1 converges by the direct comparison test. The summation n equals 1 to infinity of 1 over n factorial also converges. Okay, so that's the direct comparison test. All right, try to get it less than something that converges or bigger than something that diverges. Okay, here was our original problem. And I took each individual term and showed it was less than the nth term for the Bn series.
Professor Watt,
Yes.
I'm just confused on like the symbol. So like the exclamation point, I don't know what the real name is, but is it 1/2?
What do you mean?
The
What
word,
symbol?
like the original problem, it's 1 over n, then the symbol.
Oh, you don't know what a factorial is. Well, okay. I'm glad you asked. I guarantee you, since you asked, you are not the only one. So n factorial is a big thing for the next test we're going to do too, is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. So where did I get those numbers? I got 1 factorial was 1. 2 factorial is 2 times 1. That's how I got 2. 3 factorial is 3 times 2 times 1. That's 6. 4 factorial is 4 times 3 times 2 times 1. And that was 24. Okay, so now you see where I got these numbers. Okay, so this 2 was 2 factorial. This 6 was 3 factorial. The 24 was 4 factorial. The 120 was 5 factorial. So I was doing the factorial in each one. Okay.
Okay, thank you.
All right, something else you'll need to know for the next test is that n plus 1 factorial is the same as just taking n plus 1 and multiplying by n factorial, because n factorial gives you the product of everything up to n. So n plus 1 factorial is the product of everything up to n plus 1. So you only have to multiply all the stuff that you've already done by the next number. Okay, so we're going to use this. This is real important. We're going to use this in the next section. Okay. All right, next test. So the next test is the limit comparison test. Just a little bit wordy. Okay, so here is the limit comparison test. So now we have two series, again, summation AN and BN. And they both have positive terms. We're not talking about anything with a negative term. They both have positive terms after a certain point. So they can do whatever they want to do in the beginning, but they got to become positive at the end. Okay. If the limit as n approaches infinity of the ratio, and I mean ratio, I mean the difference, no, the division of AN over BN. If you can do AN over BN and you take that limit and you get any number L, so think of limit L, any number L, and L is obviously going to be a positive number, then they both converge or both diverge. There's two other parts. If you take the limit as n goes to infinity and you get 0 and Bn converges, then An converges. And if you take the limit as n approaches infinity of An over Bn and you get infinity, and summation Bn diverges, then summation An also has to go to infinity with it. Okay, any questions? I give you a moment to write that down. Now, this one is much more the easiest test, I think, of all of them, if you're good with limits. Okay, number one example. Okay, So now you are going to look at this, and what I want you to do, this is the one where you use the limit. So I want you to think in the limit as n goes to infinity, what would still exist? So so here's my little scratch on the side. Okay, I'm not sure which test I want to use, but I think I may want to use the limit comparison test. So on the side, I'll do 1 over 2n plus 1. And as n goes to infinity, that 1 is not as important. So it looks like 1 over 2n. Okay, so it kind of looks like that, but that kind of looks like 1/2 times 1 over n. And oh, now I think I'm going to use this because this is what it looks like as my series Bn. So what I've done is I just took out some of the stuff that's not really going to matter as n goes to infinity. Okay, so on my little scratch paper, that's what I'm thinking. So now I'm going to let my an be 1 over 2n plus 1. And I'm going to let my bn just be 1 over n. Okay. So now by this limit comparison test, we're going to look at the limit as n goes to infinity of an over bn. So that's the limit as n goes to infinity. An is 1 over 2n plus 1. So I get 1 over and that is divided by 1 over n. Okay. So now I get the limit as n approaches infinity of 1 over 2n plus 1 times n over 1. So that's the limit as n approaches infinity of n divided by 2n plus 1. And I see that limit is infinity over infinity. So this thing is right. Just screaming L'Hopital's rule. So now I get the limit as n approaches infinity of 1 over 2. And that's 1/2. So a number that's greater than 0, not equal to infinity. So by the limit comparison test, so we got a number. Now we know that the sum n equals 1 to infinity of 1 over n diverges, because it's the harmonic series. So that implies by the limit comparison test, the summation n equals 1 to infinity of 1 over 2n plus 1 also converges. Okay. Okay, so now, what does this one look like as n gets really, really big? Can anybody get an idea? I'm going to set it up for you, and then I'm going to let you do it while I take roll. Okay, so as n gets really, really big, so here's my scratch on the side again. I have the square root of n, which is n to the 1/2, divided by n squared plus 3. And as n goes to infinity, that 3 is not going to matter. So it's going to look like n to the 1/2 over n squared, which looks like 1 over n to the 3/2. Okay, so now an is the square root of n over n squared plus 3, and bn is equal to 1 over n to the 3/2. So what I want you to do is I want you to compute the limit as n approaches infinity of an divided by bn. Okay. Okay, so did anybody get that limit? Is anybody able to compute this limit?
At the last part, I got, before doing L'Hopital's rule, I got n squared over n squared plus 3. I'm not sure if that's right.
That's right.
Okay.
That's right. So you have the limit as n approaches infinity of, when I divide an by bn, I'm going to skip the middleman. When I divide an by bn, since bn is a fraction, I multiply by the reciprocal. So I'm going to get the square root of n divided by n squared plus 3. And dividing by 1 over n cubed, n to the 3/2 is the same as multiplying by n to the 3/2 over 1. So yes, Peyton, this is right. The limit as n approaches infinity of n squared over n squared plus 1. And you get infinity over infinity. So yes, we can use L'Hopital's rule. So that gives me the limit as n approaches infinity of 2n over 2n. That's just the limit of n approaches infinity of 1. That equals 1, which is greater than 0. So we can say by the limit comparison test, oh, now we know summation n equals 1 to infinity of 1 over n to the 3/2 does what? Converges or diverges? What kind of series is it? It looks like it has a certain form
Are you talking about the 1 over n
to the 3/2.
p series?
It's a p series. This thing converges by p series. P equal to 3/2, which is greater than 1. So now that we did a limit comparison test to something that converges, the other series converges. So by the limit comparison test, the summation n equals 1 to infinity of the square root of n over, what was it? N squared plus 1 converges. Okay, any questions? We are down to 1 minute, so I'm not going to be able to finish this one, as you can see. But I am going to tell you what you compare it to, or let you figure it out. Let's see. We can do that. Let's figure it out. Okay, so what's in our scratch? That's just our mind thoughts. Okay, I have 1 over 2 to the n minus 1. Uh-oh. And as n goes to infinity, that 2 to the n is going to get so big that that 1 is not going to matter. So it looks like 1 over 2 to the n. Okay, so that is what you are going to use for your comparison tests. So when we come back tomorrow, just before we start our next section on alternating series, we'll discuss whether this series, what you got, whether this series converges or diverges. Okay, any questions? Comments? All righty. I will see you guys tomorrow.
Hello.
Oh, hang on 1 second. Just trying to stop this video.